Welcome everyone. So my name is Henry Yan. I'm in Department of Chemistry. And today I'd like to tell you a little bit about chemistry, but not the chemistry in your mind conventionally. I'd like to tell you about the chemistry in some of the very exciting emerging technologies. So what is chemistry in your mind? Many of you think of this guy wearing, white lab coats, pouring solutions, doing reactions. Or many of you think of these colorful solutions and people are like playing magic. And some of you also think of big chemistry factories, plants, dangerous reactions, explosions, accidents. So some of you might be a little bit scared of chemistry in some sense. And also chemical factories in mainland China is considered one of the main pollution generators. So not the best. But some of you think of medicines, which are very important for you. And lots of these organic medicines are actually organic compounds synthesized by chemists. So this is one of the structures, and that can cure your headache. The structure is actually very simple. And if you study chemistry, you may know how you can cure diseases. It's better to have the light off. Can you keep the light off? Okay, so I could tell you modern chemistry covers a much broader scope than this. So today I'll give you a few examples of chemistry in emerging technologies. The first example is something you're very familiar with, iPad. Okay, almost everybody has an iPad, and everybody likes iPad, and including my kids. They play with the iPad, they cannot stop. But I worry. The iPad is easy to break. They play, they fight, they drop it, it's going to break. And a lot of people say, and these days the kids, their bags are too heavy. They go to school, they carry very heavy bags. Can we give them, every one of them, iPad so that they don't have to carry the bags anymore? Yes, we can do that. And some people try, especially in elementary school. Kids, they're not so careful with iPad. They drop it, they break one. That's $8,000. And then they drop another one. Parents have to spend money on 2-3 iPad every semester. They cannot afford it. So can you have flexible iPad like this? The display is totally flexible. In this example, you can even roll the display around a pencil. You can see the display is so amazing, amazingly flexible. This type of flexible display, flexible iPad, is based on a new technology called organic LED. Organic LED is invented by chemists. It's invented by a person called Chin Tan. Actually, this gentleman, he was born in Hong Kong, somewhere close to Yunnan. And he just joined us. He just joined, he spent 30 years in the United States, but Hong Kong is still his home. So now he just came back, started about 2 days ago. So if you come to HKUST, you have the, luxury of working with the inventor, the father of OLED. OLED is amazing technology. It's everywhere. It can change our life in the future, and it is changing our life now. The Samsung Galaxy cell phones are all based on OLED displays. So hopefully, in the near future, instead of having rigid iPad, we're going to have flexible iPad based on organic LED. In short, it's called OLED. I hope you can remember that name, OLED. And people estimate that in the next 20, 30 years, all the displays, all the electronics are going to become flexible because it's lighter, it's easier to carry, and it's cheaper in some sense how to produce these displays. So the flexible display is gonna, flexible electronics is gonna reach about $500 billion of market before 2014. We will see. And besides using OLED in cell phones, you can also use OLED for TV. You can see this TV is really, really thin. And I remember when I was moving my house, I had a 40-inch TV. It was so heavy, I barely want to move it. I just want to get rid of it. If you have OLED TV like this, it's as thin as a piece of paper. you can carry it using one hand. So moving TV, big TV is no longer a problem. And very recently, Samsung also announced this curved TV. You could have 3 TV, you can have 360 degree, you can watch movies in all directions. And this type of curved TV is also based on OLED technology. At this point, these are a little bit too expensive, like twice as expensive as the typical LCD display. But in the future, when chemists start to invent better materials, cheaper materials, and this type of display are going to become cheaper and cheaper. And maybe you can have this type of display in everybody's home. Okay, so that was the first example. That was an OLED-based display or electronics. The second example is about solar cell. And these days, people are very much concerned about energy and environment. If you go to Beijing in the winter, the PM 2.5 is about 1,000. It's a little bit crazy. That's because everybody is driving cars. That's because there are lots of pollutions everywhere. So I don't know if you know, we actually have a lot of energy from the sun. The energy from the sun, just in 2 hours, can supply the entire world for 3 months. So solar cell is one of the most ideal and most important renewable energy technology. If we can use solar cell to replace the other, like oil, like natural gases, then we will not have the pollution problems that we have today. So lots of you have seen this type of solar cells. This solar cell is called crystalline silicon solar cell. And it's important, and there are lots of these solar cells around, but they cannot compete with conventional fossil fuels. Let me show you this chart. This is a total energy used by the globe every year. And the contribution by solar cell is about 0.1%. It's like nothing. Nothing compared to coal, oil, or gas. It's very little. Why is that? Because these solar cells are very expensive. These solar cells are very difficult to make. Complicated procedures to make these solar cells. So when you get a solar cell panel, you have to spend $500 to buy it. Instead, it can only save you $100 of electricity. You don't want to buy it. People are very smart. They don't want to spend 5 times on their household electricity use. So these solar cells are complicated to make, and they're difficult to make, and they're expensive because of that. So we need to develop solar cell technologies that are easier to produce, and cheaper to produce, and faster to produce. So here I give you everyone a question. If you look around the products around you, what is cheap? What is easy? What is fast to produce? Can I have some volunteer to answer this question? Can you give me any example that is very easy to produce? Do you want to try? What is easy to produce?
Hydrogen.
Hydrogen. Okay, that's one example. Any other example? Any other?
How about plastics?
Plastics. Okay, plastics is cheap. Okay, so I want to tell you, this is very cheap. Newspaper printing is very cheap. Imagine how many newspapers we have every day, right? And you have a stack of newspapers, and the way to produce newspaper, you have roll of paper, you have so-called printing press, and this paper just roll along the printing press, and different colors go onto the paper. So all this process happens in about a couple of hours. So every night, you have all sorts of sports games, right? Some games are very late. When the results are all announced, and the papers, the editors print all the contents, they finalize the contents of the paper and print them in just a couple of hours. And next morning, before 5 a.m., all these papers are distributed everywhere. So newspaper printing is really fast, simple, and cheap. So can we produce solar cells like the printing of newspapers? Can we do this? Now, instead of having paper, we have a roll of plastic substrates, like polymers. Polymers are cheap. this gentleman just said. Okay, then we print solar cell materials on top. And these materials are organic materials. I want to emphasize that again, developed by chemists. And these materials can convert light to electricity, just like the conventional solar cells. So now we can make solar panels like this. So this is so-called printed solar cell or organic solar cell, or some people call it polymer solar cell. This type of solar cell has lots of advantages. And low cost, is as cheap as newspapers, and is very flexible, it's very light in weight. Remember, these old silicon solar cell panels are so heavy. To install on your roof, you have to have two big men, you know. You have to be careful. Don't get anybody injured. And lightweight. Here is a bus station in San Francisco. You can have this type of plastic solar cell at the rooftop of the bus station. So this type of solar cell is truly amazing. And some of you saying, oh, is it real? Do you really have it? Are you just imagine, you know, 50 years later? Actually, we do have it. Myself, I have one example of this real solar cell. It's made by printing. Okay? You can see the solar cell panel is very flexible. You can never imagine you can bend and roll a inorganic solar cell or silicon solar cell like this. And lots of you use a smartphone. Smartphones consume lots of energy. The battery goes out very quickly. If you carry this back, you will never have to worry about it because you're charging your cell phone all the time. And not here, but maybe outside. And now our technology are even better than what's in this bag. And now we can use this bag to charge your laptop. So that's even better. So this type of solar cell technology is real. A company called Konarka, and they built a factory. And the factory was very cheap, actually. They actually bought an old printing facility from someone else. Say, this example is very interesting for you to know. So Chinese government spent about hundreds of billions of dollars to produce so many solar cells. But this company spent about $5 million. They bought an old printing factory, and they converted this old printing factory into their plastic power plant, the organic solar cell factory. And they achieved a theoretical printing volume, production volume of 1 gigawatt. It's about 10% of the entire China's production volume. But they spent about 0.01% of the money that we spent. So this is a new type of solar cell technology that's real. And again, the content of this solar cell are organic materials. And if you're a chemist, if you're smart, you can think of what organic materials can give you this type of special properties. So that's the second example. I want to give you the third example. And some people who like to read may have seen this before. It's called e-reader, and it's black and white. And most e-readers are black and white, just like this. And my wife likes reading on it most of the time, but I don't like it very much. First of all, it's a little bit too big. I cannot put it into my pocket. You have to carry a bag all the time. I don't like it. Second of all, it's a little bit too small because it's smaller than typical books. And you don't have like 10 lines of words on it, so you have to flip the pages all the time. So it's too big and it's too small. It's just not as good as the conventional books. But how about we have this? We can have e-readers that can be folded. So you can fold it into a cell phone like this, and you can unroll it. You have a bigger display. You can read it easier. So actually, before I came back to USC, I was working in a company that's developing this type of products. This product is on market. It's real. It's just a little bit more expensive right now. And also it's black and white. We want to develop color display instead of just black and white. So this product is real. And this product will solve lots of people's problems. You can, especially in Hong Kong, you spend a lot of time on public transportation, and people always like to have the bigger display. And the bigger Samsung Galaxy cell phone, and it's too big to put in the pocket sometimes. Or iPad is too big. But if you have this, it can solve all those problems. Again, e-reader is an invention invented by chemists. And this is not conventional chemistry. This is not just about medicine, about your energy levels. And this is about how to use chemistry to design, synthesize new materials that have special and unique properties. So today I told you about several examples of these new materials. And now we will try to do a demonstration. And this demonstration was related to OLED. Related to this, OLED. And there's a professor in our department, Professor Tan, and there are two Professor Tan. The first Professor Tan, Chin Tan, born in Hong Kong, and he is the inventor of the father of OLED. The second Professor Tan is also a big guy, and in our department, he discovered a new class of material for OLED. Most of the conventional material for OLED, and they can emit in dilute solutions. They emit light in dilute solutions. But when in the real applications, the solutions are more concentrated or in solid, they don't emit light. But Professor Tan discovered a new class of material that's reversed. In the dilute solution, does not emit light. In a real situation, more concentrated solution, actually emit very bright light. So we're going to have Dr. Yilong and one of my students too, to help you demonstrate the phenomenon called aggregation-induced emission. So these are two types of materials. This material is invented by HKUST. You see, it's very bright. This material does not emit light. In real applications, you have this display and your material are in the solid state. So if your material does not emit light in solid state, this only emit light in solution. It's not really useful, right? You want your material to emit light in solid state like this. So let's try the first material. This is a bad example, conventional material. So we dump the material into this big cylinder. And this is a solvent, ethanol, that can dissolve this material. This is a conventional material. Let's see if it can emit light. Okay, let me block the screen. So it does emit light, but in solutions, in very dilute solutions. Okay, in this state, so basically here, when the molecules are separated, they can emit light. But however, in real situations, the molecules are always aggregate together. In solid film or in your body, all these molecules are staying together. So now we're going to add some bad solvent, which is hexane. So it was emitting light. You can see the bottom of the cylinder. But as soon as you add the hexane, the light gets weaker and weaker and weaker. The emission of light is gone. So this type of material is bad. It can emit light here, but this situation is very dilute solution, is not, it's not the real applicable situation. This is a real situation when you have the molecule more aggregated, but it does not emit light. So now we're going to show you our material. Again, show this material to you in a solid state. It emits light. This is really important because in most of your applications, it's actually in the solid state or the aggregated states. Okay, so now let's try to dissolve this material. In solid state, it emits light. Very nice blue color. So now we're going to dissolve it. This is a good solvent for this material. Ooh, the light is gone. You see? Now, it doesn't really matter, right? Because this is a dilute solution, even if it doesn't work, doesn't matter for us. What matters is now. Let's see if the light comes back. This is a poor solvent. When you pour in the poor solvent, wow, the light is back. And it's very bright. So now the molecules are more aggregated. It's like in the solid. See, hopefully you understand two things. In some material emit light in the solution when they're not aggregated. But that type of situation is not useful at all. Like this situation, it is not useful at all. In real solid, it does not emit light. In the aggregate states here, it does not emit light. But for this material, in the aggregate solution, it's very bright. In the solid state, it's also very bright. So this was a discovery that's completely against textbooks. And because of this type of properties, and we can use the materials developed at HKUST to make brighter displays and more stable displays. So that's the demonstration. Okay, so can you carry this? Yeah. Give us 1 minute to clean up this a little bit. And a little bit here is organic solvent, so we wanna take it away as soon as we finish. And actually, the molecule is used here very, very simple. If you have a little bit more chemistry knowledge, this molecule contains 4 benzene and a double bond in between. Extremely simple molecule. But it has the amazing property that you can never imagine if you don't have the chemistry knowledge. Okay, let's move on. So you have these examples already. And let's talk a little bit about the research in our department. In chemistry, conventional chemistry have 4 areas. In physical chemistry, here. And physical chemistry is about the fundamental and theoretical base of other chemistry areas. And it helps you explain what's going on in chemistry. Lots of the chemistry phenomena, you know, and you need to understand them. And some of them you can never explain them, but they exist. But physical chemistry tries to explain the chemistry phenomenon we see. So it's more fundamental. It's not about application, it's more fundamental. In physical chemistry, you talk about electrons, atoms, molecules, orbitals, and these make up your organic or inorganic materials. You also talk about energy levels. It decides which material is more stable, which material is not so stable. So this is a fundamental theory part of chemistry. Now for inorganic chemistry, it's typically about compounds not containing carbon or hydrogen. It's about like rocks like this from geological systems. Or here is the crystal structure of sodium chloride. It's a salt that you eat every day. So this type of compound are called inorganic compounds. Now, this is organic chemistry. Organic compounds contains carbon, hydrogen, and very often related to biological systems, like you know, molecules in your body. They're all organic. Let me give you 2 examples of organic compounds. And this is so-called polymer. It's contained carbon, hydrogen, it's plastics. Now this molecule, also it contains carbon, hydrogen with 1 metal inside. And this molecule is very important. You may not recognize this molecule, but if you don't have it, you're in trouble because it's blood. And lots of this chemistry, these molecules, how they work, and by studying the chemistry here, you will little by little understand how this chemistry works. The last subject of chemistry is so-called analytical chemistry. Analytical chemistry is the tool and to analyze different things in chemistry. And it can help organic chemistry, help inorganic chemistry, it can also help physical chemistry. So it's a tool you use in all chemistry areas. Let me give you 2 examples of analytical chemistry. One example is the Hong Kong Jockey Club. Those horses, after the races, they need to be tested. And those are typical analytical chemistry. You can test whether those horses take illegal drugs before they run the races. That's one example. And another example is, I don't know if you watched the TV show called CSI, and Crime Scene Investigation. It's one of the most popular TV shows in the United States. And graduate students, they love it. And in those is all analytical chemistry. They use analytical chemistry methods to track down criminals. So those are 4 general areas of chemistry. And so our research, our education here, we cover all areas of fundamental chemistry, physical, organic, inorganic. What happened? Okay, it came back, just like the light. Now, applied chemistry, half of our faculty members study fundamental chemistry, but we do not stop there. We want to use our chemistry knowledge to do something useful, to invent the next iPad, to invent the next solar cell technology. So in this part, one part, we use organic chemistry to make new medicines. And this part, we collaborated with the School of Life Science, and they understand human bodies, and we understand these chemical structures. So working together, we discover these new drugs that might help you cure cancers. And we work on organic electronics. We use organic materials to make the flexible iPad, to make foldable e-readers. We also use organic material to make organic solar cells. This is the example I just showed you. And these solar cells are believed to be revolutionary over the next 30, 40 years. We also study environmental science, analytical chemistry, again PM 2.5. And one of the professors in our department, she's actually setting up stations in several locations of Hong Kong to measure the PM 2.5 in Hong Kong. And can you guess which area of Hong Kong has the lowest PM 2.5? That's Clearwater Bay. And we're about 30-40% lower than Mong Kok, and compared to Hong Kong Island, where Hong Kong Island is even worse. So if you do like a nice environment, and HKUST is the best place to go. We also study inorganic chemistry, and these days inorganic chemistry is very much related to nanomaterials. Have you heard of nanotubes, nanowires, and graphenes? All of these are nanomaterials. And here we have a group of faculties work on these different applications. Okay, I had one example here. And this example is to just give you a little bit more chemistry knowledge. In previous slides, I give you examples. But now, really, I wanted to show you why these organic materials, they can conduct charges. Conventional materials, conventional electronics are based on silicon, or metals, or copper. So these materials are conductive, but conventional organic materials are like medicine or plastic. They are not conductive. So why silicon is conductive? Because in silicon, you have electrons that are not bonded to any atoms. So you have all these atoms, and these electrons are bonded, but you do have that one electron. You see this electron is not bonded to any of the molecules here. It can jump in the structure. So this is why inorganic materials can be conductive. This is why you have computers. In computers, you have silicon, doped silicon, with these electrons moving around. That's why your computer can run fast. For organic materials, however, for conventional organic materials, you have carbon, 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 single bond, single bond. For this type of organic material, electrons cannot move. Electrons are bounded within the single bond structure. Within the bond, electrons cannot go anywhere. However, if we have this type of polymer have double bond, single bond, double bond, single bond. It turns out when you have this type of structure, we call it conjugated structure, then electrons can move along the backbone of the structure very easily. So this is why organic materials can do the same thing as inorganic materials, because we invented this type of conjugating molecules. So this is a very simple example. Without the right background, it will be difficult for me to explain more about chemistry to you. And so that's pretty much all about my presentation. I still have 15 minutes. I want to just, without any slides, just tell you a little bit more about our teaching here. And here, research, UST is known for strength in research, but our teaching is also, I believe, is quite strong. And in our teaching, a lot of the students choose chemistry, but in the future, they go on, they do jobs not related to chemistry. That is okay. It's not about the chemistry knowledge you study here, that's most important. It's about the training. So when you go through these chemistry educations, you actually learn how to think. You actually learn how to do presentations. And presentation is very much similar to, in the future, you work for a manager, you need to do a report. You need to present to managers. So in one of the courses I teach right now is a final year course, and we spend about 30% of our time in the class, and students do presentations. And they do presentations, I tell them, what's the problem of your presentation? Because I came back from industry, I interview a lot of people, so I know that this type of presentation may not be good, that type of presentation may be good. So here, we do emphasize on a lot of the practical skills. What you learn here is not just chemistry. Well, if you love chemistry, that's fine, you can go to graduate school. But for some people, actually for most people, in the end, they're not going to graduate school. They find a local job, maybe related or not related to chemistry. But I found the skills you learned, the ability to learn, to think logically that you get here, that's a very important ability. My wife works in a company in the Hong Kong Island, and very often when they try to hire people, the first university you go to is UST. Because you know what they said? They said UST is University of Stress and Tension. So if you can survive this stress and tension at UST, in our company you have no problem. Our company is also the company of stress and tension. I mean, companies are like that these days, especially you want to get a high-paying job. It's extremely stressful. If you go through the training, I mean, I don't really, it's not our intention to stress you, but it's our intention to give you the best education so that when you go out there, you're capable of dealing with the situations, you have the skills, you have the abilities to deal with those situations. So that's something I'm really proud, and I'm here only for 1 year, but I'm proud of the students we educate here, and proud of the educational system we have here. And in terms of research, in case you want to choose PG as your path moving forward, and we do have a very nice research environment. If you look around UST, you find that we only have one building. So chemistry, physics, electrical engineering, everything is in here. And in modern science, the chemistry I talk about today is not only chemistry. Like students in my group, they study chemistry, but 60% of the research about electronics, because we make solar cells, we make displays. So it's not just about chemistry. You have to learn 1/3 of chemistry, 1/3 of material science, and 1/3 of electrical engineering. You have to learn everything. And HKUST is the best place to do that because we have everybody together. And can you imagine, you make some materials and you have to go to electrical engineering, which is 20 minutes away on the other side of the campus. You cannot do that. And here, all our experiment is happening in one building, and chemistry on the 7th floor, and electrical engineering on the 4th floor. You just take the elevator, you can do experiments together. And all the faculties, they can have discussion together. Students, you're surrounded by students from different disciplines. So this is so-called interdisciplinary research. This is very, very important. In modern science, there's no boundary anymore. You learn the basic knowledge. For example, you come to School of Science, you don't have to choose major. Instead, you can study chemistry, you can study physics. And for students who are really interested, you can even go into the lab. You can come to my lab, you see, oh, I want to see what chemistry research is like. You can go to the physics lab, you can see, oh, what physics research is like. And then you have 1 year to decide where you want to go. And you have a lot of time to decide. We also have interdisciplinary programs. In that program, we don't give you any restriction what course you select. Like we have PG program called Nanoscience program. And in that program, students can select any courses in physics, electrical engineering, or chemistry. So you have the freedom to do that. You can learn the things you're most interested in. You can learn the things that are most useful for you. So that's another aspect I think is very important at UST. Overall, I believe that our education can produce good people. Not just good in education or in research, but the ability to survive, to be successful in this today's society, outside, either Hong Kong, some of the people go to United States, some people find jobs in mainland China, but that's the purpose of our education. Well, thank you very much. I'll be happy to answer any question you might have. So, questions? Or if you want to touch this, you have 5 minutes to pass this around. The efficiency of this solar cell was only about 2% because this product was about 6 years old. And today in my lab, I can make 10%, 5 times higher than this. And by the way, that 10% is about the best you can do in anywhere, highest in the world.